Okay, now that the portion of the part of visualization is complete, let us focus our complete attention towards the derivation part. Now again, we will draw a couple of well, actually 3 to 4 diagrams here to ensure that the visualization that we did in 3D is translated to a paper. So we have the hemisphere which is lying along the XZ plane, such that the flat bottom, which is the circular face here, lies along the XZ, and the curved surface extends along the y-axis. See, if you have, if you were writing notes along with me, then all those things I've said right now would be there in your in the visualization of the 3D part that we've done, and things will become very clear to you if you follow the notes. Okay, so in this three-dimensional hemisphere, we consider one small disk at a height y with a thickness dy, okay, and of course radius r. Now density of this sphere, and most importantly, what do we assume here? We assume that the sphere is uniformly distributed in terms of mass. So that uniform distribution, mass density is rho, which is mass by volume. Mass assuming to be m, and the volume is 2 by 3 into pi r cube, r being radius of the sphere. So this becomes rho is equal to 3m by 2 pi r cube. Why do we need this? We will come to that in a while. Okay, and now this triangle should be very clear to you, because we already saw how did this triangle come into formation. So if we consider only one such disk at a height y and with radius x and the radius of the sphere being r, we know that x square plus y square is equal to r square, and therefore y square here will be equal to r square minus x square. Now you might be wondering, why am I taking y square and why not x square? We'll come to that in a while. Okay, now for this disk also, since the overall density rho is a constant, we can say that for this disk as well, we have rho is equal to m by v. Therefore m is equal to rho into v, and since this disk is a very small disk, the mass would be dm will be equal to rho into dv. What is dv? dv is, okay, let me just write over here, volume is area into height. Area is the circular area, which is pi r square, and therefore this becomes volume of cylinder basically as pi r square into h. Okay, so r is x, and the height is this thickness, which we earlier said to be as dy. Well, this is how the disk looks in 3D, right? So we have pi r square replaced as pi x square into h, which is dy. Exactly, that is why we express the complete equation in terms of y, because we have here dy. So what is rho? Rho from this largest hemisphere is rho is 3m by 2 pi r cube, and if we bring the same over here, what we get is dm is equal to rho replaced by 3m by 2 pi r cube into pi x square dy. X square is, okay, oh I'm so sorry, it should be the other way around here, right? Y square, it should be actually x square is equal to r square minus y square, and not y square is equal to y, because the equation is in terms of dy. My bad. So we will have x square is equal to r square minus y square. Yeah, that makes sense. Now we have this equation, dm is equal to 3m by 2 pi r cube into pi by pi is 1, r square minus y square into dy. Okay, if dm is the expression that I derived so far, what is y bar is equal to? Y bar will be equal to integral y dm by integral dm, right? And what is integral y dm? Dm is 3m by 2 pi r cube into pi. Okay, we don't need this pi here, right? Pi by pi is 1. Pi by pi is 1. Yeah. into r square minus y square dy. Now in this, if we consider these two steps alone, the only mathematical part I've done is, since mass is a constant, right, and since 3 by 2 is a constant, m is a constant, r cube is a constant, I have taken these phrases out of the integrand and written the same as 1 by m into 3 by 2 into m by r cube into integral y r square minus y square, y varying from 0 to r. Now, why do we have y varying from 0 to r? For this, you will have to go back to the to the previous solution. Why? Because we discussed things in very detail that at this point we have the value of y is equal to 0, right? And this point we have the value of, let us say, at O y is equal to 0, and at A y is equal to r. So this here represents the smallest disk, and this here represents the largest disk. So if you were to compare like this, this is one disk over here, and this is the largest disk. So that represents the variation of y from 0 to y is equal to r. Okay. Now if you understand the limits of y varying from 0 to r, we can open the bracket. So y into r square minus y square becomes integral 0 to r y r square dy minus integral 0 to r y into y square becomes y cube dy. Now, integral y r square dy has r square as a constant because r is the radius of the hemisphere, which is a constant, which therefore can be pulled out of the integrand, which becomes r square into integral 0 to r y dy and integral 0 to r y cube dy. What is integral 0 to r y dy? It is y square by 2, y cube is y to the power 4 by 4, varying from 0 to r, 0 to r. Applying the limits, we have upper limits as r and lower limit as 0. This becomes r square by 2 minus lower limit 0 square by 2 minus upper limit r to the power 4 minus 0 lower limit 0 by 4. So this becomes r square by 2 into r square minus r raised to 4 by 4. R square into r square is r to the power 4 by 2 minus r to the power 4 by 4. Now for the ease of calculation, I'll multiply a 2 in both numerator and denominator. This becomes 2 r to the power 4 by 4 minus r to the power 4 by 4. Now we have the common denominator. 2r raised to 4 minus r raised to 4 is, 2r raised to 4 minus r raised to 4 is r raised to 4 by 4. Now r cube, r raised to 4 by r cube is, r raised to 4 by r cube is, okay, I've grouped r raised to 4 and r cube here. 3 by 2 into 4. So this becomes 3 by 8 into r raised to 4 by r cube is r, and therefore we come to the original place where we started this, the initial place where we started this derivation overall. So the y bar is equal to 3 by 8 into r, and since r is equal to 8, we have y bar is equal to 3. Okay, so I do understand that this is very intensive derivation, because you visualize things in 3D and then you apply the concept that we learned in class 11th in your mathematics, three-dimensional figures, and then you bring all those concepts together and integrate from y is equal to 0 to r, drive it to conclusion, and we are not done yet. Why? Because all this discussion was done with respect to figure the base lying on xz plane and height along the y-axis. We will discuss in detail what happens when this becomes xy varying along z-axis and yz and height varying along x-axis. And then when we'll compare these three, things will become really clear to you, and you'll be able to solve any question that comes out of hemisphere, or for that matter even the complete sphere. Okay. All right. So let's now move on to, we'll do a couple of other questions, and then we'll come back to the analysis of these three separately.